Hello, my dear students, and we continue our studies of Introduction to Major or Introduction to Aerospace Engineering. Now, class 2. Where we stopped yesterday at? Yesterday we talked about flight principles, remind you, and it's a period that usually all the aircraft, according to the nature of it, divided into 4 big groups: ballistic aircraft, aerostatical, rocket dynamical, aerodynamical. And as I said, you next time we are talking mostly about aerodynamical types of aircraft. But first we need to talk before we goes to explanation of aircraft arrangement and how it's fly to the basics of flight dynamics. First, we need to talk about basics of aerodynamics at all and basics of airfoils, flow around airfoils. Yesterday, you have already seen, at least partially, those things. First, we have talked about the Daniel Bernoulli, who have stated the relation between pressure and speed in fluid flow. And his studies, he studied different cross-section in pipes and how pressure depends on speed inside of these different cross-sections. And what is derivation from this Bernoulli principle, from this partial case of energy conservation principle, actually, that in each place of streamline, in each cross-section of streamline, energy which may be divided into kinetic energy, potential energy, and pressure is the same. Components may vary in values, but general amount of energy is the same. And that is an explanation also as a period appearing of the lift in the airfoil. But as you have already seen, this explanation is not correct. Really, as a period, lift doesn't work like this. The very first who worked with such things, as you have heard already yesterday and maybe know it before me even, it was Isaac Newton, the famous one who maybe maybe that some field of physics, some field of mechanics even called after the Newton. We have so-called Newton mechanics and relative mechanics. And whatever basic his law and his work were, in these studies, he was not completely correct. First, when he studied the flow around different objects, he proposed formulas. Now you see these formulas as Zhukovsky formulas in my slide. Wait a second. Let me do it greater in size. You see it. Zhukovsky formula for lift and drag. In our textbooks, in our country, they are called Zhukovsky formula for lift and for drag. But originally, similar formulas were written down by Newton. What is given in these formulas? As you might see, we have for lift kinetic energy of the stream, as we have seen already yesterday, area of cross-section, and some coefficient, some dimensionless coefficient. Newton has proposed formula in such a way also, but it should be said he has not studied this coefficient at all. Do forgive me, I forgot to check the time. Time is when to finish. Thanks to our ear alarm, I recollected about time. And yes, we see kinetic energy, some dimensionless coefficient, and area of the wing. Because when it's proposed, when it's given for cross section at all, for this cross section, this value it's not necessary. That is formula not for cross section already. Next, here we have, what do we have here? You see the same kinetic energy for drag. We have dimensionless coefficient and so-called cross section of middle. No, usually it comes about the, no, it's like normal cross section. If it comes about the real wing, not about endless wing, by the word, this formulas, they are for endless wing, so for theoretical case of flow. And it comes about horizontal and vertical areas of this endless airfoil. Well, let's continue once again with these formulas. And what I said yesterday, that one is not correct. It's easy to understand, yes, that why this additional force has appeared, why difference of pressure has appeared. Because of longer path in the airfoil at the top, streamline path, velocity there is higher, and due to this, pressure is a little bit less than under the wing, under the airfoil. And this difference of pressure creates lifts. But really, this explanation is not correct. And these Newton formulas in that way that they've been written down in 18th century, they give unrealistic results, actually. And they are not scientifically correct as a period. And people who try to who try to create, design airplanes according, making calculations according to this formula, they've been usually they've been unsuccessful in this meaning. And only in beginning of at the beginning of 20th century, as I said, you has appeared mathematically proven explanation and mathematically proven theory about airfoils. And actually those airfoils, like we get used to what they looks like, they start appearing after Zhukovsky and Kuta work, especially after Zhukovsky work, because it became possible to calculate mathematically the shapes of those airfoils. What this Zhukovsky-Kuta theorem is about? No, you see now a couple of formulas. These formulas, in contrary to a simple and understandable formula for lift and formula for drag that you have seen before, it's rather difficult to understand, and it's difficult to imagine what they comes about. You see, such formula for lift, it state the relations between density of streamline, density of media, density of flow, and between the speed of undisturbed streamlines, so-called, it comes about some place which where the profile is not intruded yet. The length perimeter actually of this profile and so-called circulation of speed or circulation of velocity along this profile. What does it mean? No, in the plainest word, the fluid represented in the view, like superposition of two motions. One motion is the motion of fluid itself and its linear motion, and another motion is circular motion around the airfoil. It's something like airfoil. It's replaced with such complex shaped tornado. No, of course, it shouldn't be confused, mix it up with those things, but you understand maybe already, if you have already started aerodynamics, it's the way how to model, how to simulate correctly those things in order to be able to get correct values of lift theoretically, let's say. And actually, physical understanding, physical meaning of this value circulation. Here it's given like sum of speeds along some. Actually, it's integral. It's linear integral by closed contour. This closed contour is represented. You see, like P is the S, and the whole interesting sounds. Thank you. Around and this contour length, the whole length, it's given in the next formula that we see as the first one for the lift. Just great. Guys, don't be confused with these sounds if you hear them. Something flow over the home. I hope it's not a rocket. I hope it was an airplane and it was our airplane, but maybe it's a rocket. Так. Now, let's continue. Well, I've been found some pictures in order to illustrate my words. Do pay attention what Newton and next Bernoulli and next other scientists, including Joukowsky, what they've been studying, what they looks like, these studies. Actually, you might see now this scheme of flow, of interaction of different objects, different shapes with the flow. And what do we see? We see so-called undisturbed streamlines and streamlines which flow around the body. Yes, it was rocket. Sorry. Not close to my home. No. Whatsoever. It was rocket shoving. Sorry. A bit loose my mind. Look at this. Streamlines, when they meet the plate, you see, they create the different pressure in front of this plate and behind of this plate. They are designated with signs, you see, plus, minus. And also it's symbolically, just great, symbolically given something like vortex behind of the plate and behind of the sphere. And quite clear that this vortex, actually, those people, they've been mostly interested in the studying of the drag, as I already said you. And it's obvious that shape, in their studies, they understood that shape is responsible, and they have proven it, shape is responsible for less or greater drag. And of course, they've been searching for the, let's say, ideal shapes. And in their studies, they understood that the best shape is something like this, like this drop, let's say, drop, but horizontal drop. But also it was noted that position of this profile, of this drop, it's also important. Position with respect to streamlines. It's appeared that depending on position of this shape of this, not airfoil yet, but some shape, with respect to streamlines, forces are changing significantly. No, at that moment it was not studied. It was only stated that there is dependence between such things. And here we already have, you see, it's designated like alpha, angle between the streamlines, these undisturbed streamlines under the flow, angle between the flow streamlines and angle between the some middle line of this object. What is this middle line? We yet don't know, but we're going to talk about. And just one more scheme that explain the same things as we might see. And certainly it's appeared that shape affect the values of drag and values of lift. Some side forces which may appear in case the body is not symmetrical. What was wrong in Newton's theory and what Bernoulli has changed, has detailed that not only the front shape responsible for the values of drag and values of, maybe I should switch off this signs for you. For the values of drag and for the values of lift, but also back surface is responsible for the shape. Oh, so don't forgive me, for the values of these forces. And what was stated already then, that better if the back side of the object has something like sharp edge, trailing edge should be thin and sharp. What is illustrated like some vortex here and like arrows in this picture? Actually, it's a different in boundary layer. Once again, streamlines, undisturbed streamlines, somewhere here. In ideal model of fluids, of course, it's not important, but in real fluids, there is so-called viscosity, something like inner friction. And additionally, there is a friction between streamlines, between fluid and between the object which is poured in this fluid or gas. And near the object itself exists so-called boundary layer. Boundary layer, depending on the speed and depending on the viscosity of the liquid itself, may be different. That is illustrated with the stream of water in different places and with fumes over the candle. What do we see? Like very beautiful thin flow. It's so-called laminar flow. What do we see as some bubbling water stream? It's so-called clean tubular flow. And here, as you see, smokes change, these fumes, this smoke, it changed from laminar to tubular. It doesn't matter why. Just we need to remember these effects. We need to remember these words. And sorry, I did it a bit wrong. And by the word about fumes, how to study actually how people might see these streamlines. I said they studied it. They didn't imagine it. How? No, there are some ways to do it, and the most simple way, of course, is to use smoke. When it comes about gases, in front of this object, it will be placed in the pipe with some holes, of course, and these holes, they are given the scene in the whole massive of air, some another gas. They will do little thin pipes, let's say, of smoke, little streamlines of smoke. One way. One more way is to add some painting matters into water in case we are studying liquids. One more way, additional way, but complex, is to use threads. Threads are glued immediately to long silk threads, usually glued immediately to the surface in order to study their behavior, how they show something behind this profile also, but quite clear they do not show the whole changing of streamlines around the profile. But actually, it's maybe studied, and by results of these studies, people do those charts a priori, and in each cross section it may be measured velocity, pressure, velocity, and so on in each cross section along the profile. And when they are measured, we have such resulting charts of distribution of velocity and pressure over the upper and bottom surface of profile, or some another object that pour it into liquid or into gas, or into some fluid. So first, people starts with experimental studies, as you might see, but next, of course, they'd like to have clean formulas, clean theories, let's say, that helps to calculate something, to predict some values without any additional efforts for natural experiments. And here is no, it's not quite the same you see on the left and on the right. Yeah? Here is you see some real experimental photos which demonstrate how this and taken by different methods of experimental studies, quite clear, and they demonstrate how the streamline, how the flow around the object depends on the shape of the object. And I should say that, of course, it's also with different speeds, different velocities of streamlines. Quite clear when we have laminar boundary layer, it's not very high velocity here. And here, what in this sharp wedge-like profile, you see there supersonic picture for typical for supersonic sharp changing of pressure in this place. And what is shown on the right, after obtaining such charts, such ethers for pressure all over the surface, it's possible to find so-called resulting force. Resulting force, and this resulting force, no, I didn't mention it at least once. Forces may be forces we work with, we are talking about. They may be, let's say, superficial and volumetric. When it comes about aerodynamical surfaces, aerodynamical forces, they are superficial. They are applied only onto the surface. Buoyancy force in aerostatical principle, it was also superficial force. Drag, lift, they are a result of contact of surface with the media around. And in that two cases, I mean. When it comes about their gravity, for instance, it's so-called volumetric mass force, which applied to the each little elementary volume of the matter of this profile. When we're talking about the aerodynamical forces, we consider only outer surface. I hope you understand. But somewhere this outer surface might have something, resulting point, something like center of gravity. We get used to talk that center of gravity of contour itself, and such a point where resulting force of all the superficial forces to the profile is applied, it's called center of pressure. It's the sort of central point for this profile. And what is a period? For each profile above the all, this place of center of pressure, it's different for each shape of profile, whether it's sphere or plate or airfoil. For each object, this point is different. But moreover, this point is appeared not stable. With changing of angle of attack, angle which shows the position of profile with respect to the horizon or with respect to streamlines. So usually we should draw these streamlines horizon. It also may flow a bit to the front, to the back. So it's changing a bit. And not only the value, but angle, like deviation of this force with respect to the vertical line, with respect to the chord of the airfoil, it's also different, depending on the shape, depending on the angle of attack, and depending on velocity also. Now you see some no pictures, illustrations to my words. Да. And once again, some point where the resulting aerodynamical force is applied, it's center of pressure. And center of pressure is not permanent, it may change. But there is a point which is permanent for each profile. Such a point is called focus, and focus is a point where moment of all the aerodynamical force with respect to this point, moment of resulting forces aerodynamical will be equal to zero. And in each profile, such a point is the same all over the changing of spatial position of profile. Such a point is called focus. Usually we do working and talking about this center of pressure in our, at least studies of basic things. No? And do remember that center of pressure of profile is depend. No, at least for us, we should remember it depends on the shape. Of course, it also depends on the position of profile with respect to the horizon, and it depends on some another factors. And when we're talking about real airplane consists of real parts, real things, and not all of them made of the same materials, of the same density. Moreover, you understand that a lot of different places in the wing, for instance, they are empty, just empty, and there is no weight. No, there is a weight of air inside. And center of gravity of this real airfoil, of real wing, and center of pressure, it's not the same. If even we imagine that this airfoil, the whole area of airfoil made of some material, and this material is uniform everywhere, in each point we have some material, center of gravity and center of pressure, they don't coincide. No, maybe some case may happen when there's like merging at some moments, but really they do not coincide. Center of pressure and center of gravity. No, the center of gravity is far, 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 yet we are not even talking about center of pressure. We just have stated, let's say, such a concept, does it? This point is exist. Да. And let's come back to what I've been searching for long to find something like this, such photos, in order you might see. No, I hope if you already studied aerodynamics, wherever you studied it, you already met such things. You already seen these experimental photos of different cases of flow around there, different objects. On the left, right now on the left we see profile, and profile usually is called airfoil, and we see how it's streamlined, how it's flowed around with these fluids and with these streamlines. Very important moment. No, as I said already, boundary layer, it's in real. Sorry. Oh, here it is. In real liquid, in real gas, there is so-called boundary level, and it's visible that by these charts, it's visible that at their surface itself, it's a full breaking of flow. It's there is no flow actually there. Right? It's zero. And on some distance, we see it's already with appropriate values. Let's come back. What? And boundary layer may be either laminar, practically no drag. No, it's not like this, of course, but practically no drag, comparatively to the turbulent one. And the place where the boundary layer has changed sharply, such a place it's called point of separation. What right now you see what happened, point of separation, so-called here, And something like vortexes, they appeared behind, no, like between the laminar flow and not boundary layer already, but between some laminar flow of undisturbed streamlines and between the profile, between the surface of the airfoil. Whether it's good or not, that is the question. Actually, in the planius world, it's not good. But laminar flow above the wall, it has less drag and it has stable value of lift. And that one, it's much less much less predictable, let's say, in its behavior. And actually, there is appearing of dangerous situation over the airfoil, as you see. In this place, when such point of separation, it's maybe somewhere here on profile, what for instance, in different angles of attack, it may be somewhere at the more close to the trailing edge, for instance. But when it's travel already to beginning of the airfoil, it's resulted usually in sharp reducing of the lift itself, increasing of the drag and reducing of the lift. Just remember this fact for a while, and next we will talk about. And here is the thin plate you see in laminar flow, and the different viscosity of the flow itself, different speed and different viscosity. And we see demonstration of laminar flow around the plate, and the same plate even with the same angle of attack, but already it has turbulent flow behind of it. Depending on the velocity and, as I said, viscosity of the liquid. Here is demonstration of laminar turbulent flow on a sphere, inside of some liquid, and again thin plate, and we see what. Look at this. Oi, 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 oi. I hope it will be visible better. Not completely laminar the flow is. You see some sort of vortexes at the end. You see some sort like separation of flow at the beginning also. And its angle of attack 2.5 degree. And when angle of attack is increased, you see what happened. It's completely like teared off this flow from the surface of the plate. And of course, it will be resulted in sharp reducing of the lift. And how to consider these factors, actually, how to take into account these factors in the formulas that we have seen before. We will not use this formula. It's too much complicated for us right now. We will use this formula. How those effects are taken into account in this formula. Here is dimensionless coefficients, as I said you. This coefficient is coefficient of lift, and this coefficient of drag. And these coefficients, they are usually represented in the view of special charts. They may be given like in tabular way, like table for that or another profile, or they may be given in the view of charts, what is also very convenient to use. Something like diagrams. Let's come back to our slides, to the place where we have been. Oh, no, where you disappear? No, right now, what do you see? You see different profiles which appear. Different profiles which so-called even historical profiles. No, as we have not talked about those persons yet, maybe not all of them familiar to you, maybe you already know these names. No, above all the Wright brothers airplane. Look what looks like the airfoil of Wright brothers airplane, the top one, and here is what also on the top. Next, you see also next one, Blériot. also rather thin one. And to pay attention, they are all curvative. They all with very high curvature. More similar to the just top surface of modern airplane, modern airfoils, if you understand. I trust you understand. The profile that was practically theoretically the shape of profile obtained by Zhukovsky, calculated by Zhukovsky using his theorem about circulation, and he used something like a conform transformation of cylinder in the flow, and the most effective shape of profile he has calculated. Zhukovsky profile, don't be confused with different writing down of his family name, his surname. I was also much surprised that I never thought about. I get used to see the name of Zhukovsky in English like it's given in our was given in our old official name, and I've seen it in books. And it's appeared that in the space of internet there are at least 4 different variants of transliteration of Zhukovsky's surname to different, with different letters. Zhukovsky profile, as you might see here, rather thick at the front, but all profiles, all over profiles, they compulsory airfoils. They compulsory have this sharp trailing edge. And and literally one more word, how the aerodynamical characteristics usually studied, how those things, those coefficients may be studied in special. It's not even device. But the first version, they may be called like device because it's something like device. Modern wind tunnels, they are complex. It's the whole technical complex, technical systems. And such wind tunnels, they have closed loop of gas, of air circulating in this closed loop, and somewhere in this loop it's placed model. It's maybe of course a full scaled model, but typically we use scaled model to study aerodynamical characteristics. It's already theoretically proven that the same profile, depending on the shape of profile, it has some aerodynamical contours characteristic. But if you increase it or reduce it with the same shape, these coefficients, they does not change. They depends only on shape and on position of profile in space, angle of attack. No, and the whole force, of course, depends on the speed, on velocity of streamline and of air around it, and depends on the what the type of gas you use due to density of this flow. And also it's necessary to remember, I said we will talk about, but we yet not talk about, but trust you understand that atmosphere parameters, they are not the same in different height. Near the ground, we have specific density. Next, this density with the higher, the less. And as a result, we have another temperature. As a result, we have another speed of sound on different heights, and so on. So if we talking about the whole value of force, it's important what is the density. If we're talking only about aerodynamical characteristic of profile, those things they are not affecting right now to aerodynamical characteristic of airfoil of profile. And let's talk about airfoils. Wait a second, we need some another place. Must be this one, I hope. Yes, this one with illustrations. Now, above the all, let me just show you clearly. Now, here is aerodynamical airfoil. What it typically looks like, you see. Typically, it's a little bit, no, typically. It should be also said that depending on the speed this airfoil will be used in, uh, it's not so typical. That one is typical subsonic airfoil. What does it mean, subsonic, supersonic? A bit later. Uh, Shape is rather specific. This shape has so-called camber. Camber, this curvature, you see camber upper surface camber, lower surface camber, and there is so-called mean camber or curvature, and this mean camber is represented with the line which in equal distance from the top surface to the bottom surface. Here is this line. I follow with the pointer right now. But no, it's mean camber, so-called. And there is important characteristics also of profile, which is called chord. Oh, do forgive me. No, okay, let's leave this one. Yeah. And no, here it's even better visible where the mean camber, where the chord. Chord is the distance between the very first point, very left point of profile of airfoil, and between the very right point of profile. It's like distance from beginning to the end. And chord is a piece of straight line, always. Usually, to characterize profile shape, usually in tabular way, we are using so-called percentage of the chord. For instance, 10%, 20%, and so on. And profile theoretical table usually looks like, well, maybe you have seen it already in aerodynamics if you studied it. That position of upper camber and lower camber specific points also given in persons of chord. Chord usually designated like with letter B, big. No, to be little here, do forgive me, usually as B, big. Так. As to their positioning of this airfoil in space. Right now we see airfoil in streamlines. Once again, it's compulsory should have sharp trailing edge. Leading edge may be a bit circular, maybe also sharp, depending on type of profile. Profiles for supersonic speeds, they usually sharp here. That one more typical for subsonic aircraft. And angle between vector or direction of undisturbed streamlines and between the chord of airfoil, this angle is called angle of attack. No, actually, that's it. We need to understand by now. And let's come back to these formulas. I said we need to understand how shape, how angle of attack, and other characteristics affect the lift itself. As I said, Newton at his time he proposed some to use some dimensionless coefficient there in formula, but he doesn't explain neither what it depends on, nor gave some particular values. No, maybe it was not the point of his study at all, by that time. Right now, let's try to understand what these coefficients they looks like. Typically, the chart of such coefficient looks like what you see it right now. Sorry, let's try to arrange it a bit better. this screen, its dependence of coefficients cy, coefficient of lift, dependence on the angle of attack, you see. Do pay attention, neither speed is mentioned, no density, no anything else, only on angle of attack. And what we might see, no, I should say that one for non-symmetrical profile, certainly. How may I understand it? Let's come back to that picture where we've seen different shapes, flow of different on different shapes, and where we have symmetrical profile, there is no side forces appear. Forces will be equal with from all the sides. Forces will be equal in case this symmetrical profile is not deviated with respect to the horizontal. No forces practically. No, look, it's not quite the same what I'm trying to explain, because this profile is not symmetrical. But at the top chart, you see that these forces from the top and from the bottom, they are almost equal. In case it's symmetrical, these two charts will be completely equal, completely identical, and there is no any side forces, no any light, forgive me, no any lift will be. Drag exists, but lift in this case does not exist. And what does it mean in this chart? If we have symmetrical profile, this chart comes through the zero. At zero angle of attack, it will be zero coefficient of lift. That one certainly is not symmetrical. And to pay attention, at some place, it's linear dependence. Seems like the more the better. The more angle of attack, let's see this picture, the more angle of attack, the better. Yes? Yes, but experimental studies shows what? We have seen it already. The more angle of attack may be resulted in appearance of another flow, another type of flow in boundary layer. And this another flow, which is which depends on separation point of the value, let's say, of this unpleasant turbulent flow in the boundary layer, depends on where the separation point, how close it to the front leading edge. It will be resulted in reducing of, jumping like a frog, reducing of lift. Here we see already some area where the lift is gradually reduced. It's already different from the straight line. So this rule, the more the better, since some moment it already does not exist, doesn't work. And at some moment, the coefficient of lift and lift itself as a whole at a real wing, it will be maximum. And seems like it's very, very efficient point, very good point, because we have more lift, maximum lift at this point. But actually this point is very dangerous. What might happen next? You see sharp reducing of lift, extremely sharp, with little changing of with elementary changing of angle of attack, with literally half of degree, for instance, because of different factors. Real airplane, it's not ideal object that we may imagine and which we may simulate somewhere in computer system. Real airplane may have different friction on the surface in different places of the wing, just because different coating, for instance, different ways of manufacturing, and different weather conditions whatsoever. So real airplane, it's not ideal airplane. And this non-ideal surface may show you very bad surprise in case you are using angle of attack close to so-called alpha critical crucial angle of attack. In this case, you are risking to have such effect as a stall. Stall, it's sharp its motion of the airplane due to this sharp reducing of the lift and traveling of this point of separation due to separation of flow from the surface of the wing of the airfoil. Well, to remember that this coefficient chart, it looks like look like hook actually, something like hook. You see, it has straight area, straight place line, and next it's finished with this typical area where force is reduced sharply. And of course, they should be studied for each profile, for each particular profile. And of course, they next exist in like information that supplied to designers, and it's studied in aerodynamical laboratories, as I'm already mentioned it. Not much explaining, but at least we mentioned it. Yes, that we have special technical complexes, so-called wind tunnels, where we may study aerodynamical characteristics of the wing. And these aerodynamical characteristics for us, above the all, represented what with coefficient of lift and coefficient of drag. So coefficient of lift typically looks like this. How coefficient of drag typically looks like? Let's see. What right now we see in the same coordinate system. So depends on angle of attack. We see the chart of coefficient of lift Cy and coefficient of drag Cx. But the truth is that coefficient of drag depends significantly not only on the angle of attack. I'm not talking about now about real sizes of the airplane, about something else, but drag, it's considered like consisting of some different kinds of the drag. Above the all, we have drag due to the friction, air friction over the surface. Next, we have drag, which may be induced by this turbulent boundary layer. It's already another type of drag. It's appearing at some moment only, depending on the angle of attack. Next, we have drag to the changing of velocity and changing of air viscosity. In ideal case, as I said, it's considered, it's studied that ideal liquid, ideal fluid, it's incompressible. And when it comes about liquids, like water, for instance, or some oil, they are practically incompressible. But when it comes about gases are compressible. And due to this, it's appeared a lot of additional effects. And with changing the speed, the properties, let's say, of the air itself, they are also changing. With changing the speed of motion of airfoil through the media. Wait a second. What typical diagram you see now? Typical diagram of drag, but it's already independence on speed. Speed here is designated not like V, like we get used to. It's designated in Mach number. We'll explain. And also what we might see, it depends on the shape of airplane, as it's visible here, but depends on the shape of the wing itself. Not even, what in this case is considered not even for the shape of profile. It's the shape, outer shapes of airplane, outer shapes of the wing. So drag is much more complex matter than seems like, at least, much more complex story than when we're talking about the coefficient of lift. But in general, you see the, wait a second, you see, where you see it? Here. In general, you see the more angle of attack here, yes, the more drag. Do pay attention, here it's not less angle of attack. It's just like anti-airfoil. It's like, do imagine that the same airfoil, it's rotated with the nose down, with the trailing edge higher than leading edge. And the same story, you see, there is no zero drag, let's say. Practically no zero drag. If lift may be zero at some point, drag can't be zero, because always it exists some friction of air, of whatsoever fluid over the surface. Well, and how to choose the best angle of attack? How the most efficient, the optimum angle of attack? And in this meaning, it should help us another characteristics. Actually, we have aerodynamical characteristic of airfoil, as I said you, Cy, coefficient of lift, and coefficient of Cx, coefficient of drag. And we have one more combined characteristic, which is called aerodynamical quality of airfoil. Until we here, do pay attention. The picture that I lost, seems like symmetrical airfoil, and you see distribution of pressure over and under the airfoil. Symmetrical airfoil with zero angle of attack. And the same airfoil, but a little bit rotated to some angle of attack. You want to pay attention what it looks like, how it's maybe represented. No, of course, it's not real. It's without values, as you might see. It's some qualitative explanation of what it looks like. So what it looks like? Symmetrical has zero lift in the zero angle of attack. Non-symmetrical, in case it has positive camber, upper camber higher than lower camber in value, it looks like this. If it's rotated, let me to show it in Paint instead of trying to use words, better to draw it. Yes, to draw first something like place for diagram. Well, maybe I should place it a bit here. What, and in case we have symmetrical airfoil, I hope it will be close to airfoil and it will be symmetrical. Usual normal airfoil, let's say, non-symmetrical, like this. And do imagine the same airfoil, but it's maybe rotated like this. By the word, it's not a joke. Such airfoils exist, and they exist simultaneously in the airplane, this one and that one, that we will talk about next time, maybe in a time, and you will understand what it's for. And certainly it's clear that this one has chart like this, comes through the 0 point when it comes about Cy. If we working with this, let's say normal one, it has lift even in some point. By the word, this angle deviation of this declining of this chart with respect to the horizontal also different, quite clear for different airfoils shapes, and it has some lift even when we have zero angle of attack. And for some airfoils seems like it's maybe even negative negative force. No, you see, when it's in normal position when it's normal angle of attack, on zero angle of attack, because this airfoil, as I said you, it has anti-shape, let's say, shape rotated, flipped. Well, let's kill this chart. After we have seen it, we don't need it. And let's come back to this story once again. No, here is a little picture. Maybe I should increase it, but I'm afraid the general quality of this picture is not so good. In this little picture, it's demonstrated how these charts of pressure change depending on the angle of attack. I hope you understood it. And what else? This CY depends on. When it comes only about airfoil of endless wing, it depends on shape of an airfoil and on angle of attack. But what it comes about real airplane, no, like it was, for instance, with drag coefficient. In this case, surprise, yes, in this case, what now we see symbolically the wing, straight wing, red line, and swept wing. And it's appeared that depending on the shape of the wing, with the same airfoils, with the same angles of attacks, and so on, with the same parameters, they have different aerodynamical characteristic of the wing. Not for particular airfoil, but aerodynamical characteristic as a whole wing. And what is better, seems like? No, above the all, you see the seems like on the little angle of attack, blue one is worse because it has less lift. But what is better? Better that on big angle of attacks, you see, it's more effective. Where this one has been already stalled, this wing, I mean, it's already lose all the lift and maybe it's already crushed by the moment. Until this one, it's yet not in danger. No? You see, affecting of the shape of the wing as a whole to this aerodynamical characteristic. By the word, it's so-called straight wing, it's so-called swept wing. It's like pull it back. You see the these airfoils, they are not placed along one line, да? They like deviated, no, like hands that you rotates somewhere to the back, for instance. Вот. Also, there are such characteristics that we yet don't know of the wing as a whole. Why we yet don't know it? No, because maybe you have not studied it. Maybe you already studied it in some other disciplines, as you are not really children, as far as I understand. Characteristics which are called span and relative thickness of the wing. Do pay attention. No, relative thickness may be considered like the shape of airfoil yet. Yes. You see, for thinner airfoils, we have less less efficient, in my opinion, and in opinion those who operate airplane pilots, less efficient characteristic. Yes, it's higher, seems like it's higher on rather low angle of attack, but it has very low angle alpha crucial. So it's more dangerous in this meaning. And for thicker airfoils, this point is pulled much far. This point is this separation of the flow may happen later. So thicker airfoils looks like they are more appropriate for big angles of attack. And as a result, they also give the higher lift. Here is the span. Span, it's ratio between the value of chord, no, between this value, and value of the wing length. Span practically is the ratio between this value and that value. Of course, in case of swept wing, or in case of drape wing, which looks like drape, this characteristic is not directly calculated like value of chord to the value of or relative span. Do forgive me, it's relative span. Span is the whole length here. And when it's more complex shape of the wing, it's not so directly calculated. No, the general idea is visible here. No? The longer, no, relatively longer wings, here you see the shorter wing, red one, it's shorter, and the blue one, lambda one, it's less. Да? Ой, do forgive me, maybe I did mistake. No, relative span, yes, relative span affecting like better gliders, they have more span, relative span. And maybe it's some mistake here. Maybe L2, red one, no, maybe it's not mistake. Maybe I'm mistaken. And this relative span, it's, we might seen it even in our already opened lectures. Where we've been talking about gliders. No, it's obviously, look, but for instance here, the glider picture with long and rather thin, not thin, but I mean chord is not big. And here is this relative span, it's much greater. Да? And the military airplanes, maneuverable airplanes, they are with shortest relative span. They have rather short wings comparatively to gliders, for instance. They practically have no wings. And aerodynamical characteristics of such wing with long span, they are much different from aerodynamical characteristics of shorter span. And these short-winged airplanes, they has more maneuverability, but the horizontal flight is more effective in these long-spanned airplanes. Well, about aerodynamical characteristic, let me to see the time. No time we yet have, I think. Aerodynamical characteristics of airfoil, I hope it's clear. Now, what they depends on, once again, above the all, on the shape of profile itself. Next, on position of profile in the space, of angle of attack. But it's appeared also that some characteristics like drag, for instance, depends not only on the shape and angle of attack, they also significantly depends on the speed and on the general shape of the airplane, including all this relative span, relative thickness, and so on. Next, I said we have one more characteristic, which is like hybrid characteristic. This hybrid characteristic, it's like to help us to select better effective, the most effective, the better modes, the better regimes of flight. Look, here is characteristic which is called polar, and it's characteristic which show for each particular angle of attack, what you see angles of attack, but they are not coordinate system. Coordinate system for polar is coefficient of lift with respect to coefficient of drag in different angles of attack. You see, coefficient of lift, coefficient of drag. And quite clear where will be the best place in such a polar. If we draw a line from zero tangent to this polar may have usually they looks like this, but actually they may looks different. I have found some real one in internet, I will show you. and they may look different, but usually they looks like this letter C, like half a loop, something like this. And to find the best angle of attack, the best possible, the most effective for flight position of this airfoil is possible using such a polar by simple tangent line. Do draw tangent line, and where you have the point of intersection of this polar with tangent line, it will be from zero, of course. It will be the most effective angle of attack with maximum speed, maximum lift, and drag will be optimum at this regime. And what it looks like, it's so-called aerodynamical quality of the aircraft and of the airfoil. No, usually we talk about the aerodynamical quality of the aircraft as a whole. I'm already said you, because you've seen in these diagrams that aerodynamical characteristics of the airfoil, they may also depend on what is the shape of the wing, how these airfoils, how they located with respect to each other. Next, aerodynamical characteristic may depend on speed. When it comes about drag, it's very important to remember that they depend also on speed, and so on. So usually we're talking about the quality of the airplane as a whole. Well, and practically you see it's lift to the drag ratio, but practically if we come back, can we back to the formulas, Zhukovsky formulas. No, Newton-Zhukovsky, like it's given in Western literature. If we come back to these formulas, we may see that practically it comes about the same. And in the first approximation, it's maybe assessed like coefficient of lift to coefficient of drag. What are the values of this aerodynamical quality? Quite clear. They may start from zero. If you have zero lift, you have zero quality. But usually it comes about the values like approximately modern passenger airplanes. I do not remember values for historical airplanes. In case I meet it, I will inform you about. But modern passenger airplanes, they already aerodynamically perfectized, let's say. They have such values approximately 8, 9, 10. Approximately. Modern so-called maneuverable airplanes, usually it comes about military airplanes like fighters, attack airplanes, and so on. Usually they are with this aerodynamical quality in the range from 15 to 20. By now, the best quality of airplanes, not really aerodynamically perfect airplanes, usually it comes about so-called aerobatic airplanes, which used for aerobatic exercises, for all this show, for all this impressive flights. These aerodynamically perfect airplanes, they have quality up to 25. 25, 20, maybe 7 by now is maximum. And what about another flying objects? I didn't found. No, actually, I'm not searching for the picture of one of sea birds, albatross. Do forgive me, maybe I forgot to check what is the name in English. And this bird, it has aerodynamical quality, but just a bird. Once again, passenger airplanes, 8, 10. Military airplanes, approximately 15, approximately. The best are up to 18, 20. The most perfect airplanes made by human, they are up to 25 in aerodynamical quality, and a bird who flying over the sea, 40. It's twice better aerodynamically than any airplane we have been created. Just be impressed with this fact. Well, так, it's too early for us. Where we are. Вот. Да. And after you have some idea about these aerodynamical coefficients, about how to calculate lift, let's try to imagine, no, once I'm already said, one point, I promised to show you a couple more polars. One point, what for those things are necessary, these charts, these diagrams. No, of course, for calculations of lift, calculation of drag, and so on, for real airplanes. Why we need this hybrid coefficient, hybrid ratio, quality of the airplane? It might help us to select the better position of our airfoils, position of airplane in a space, seems like, because it might help you to understand where the best ratio, where the best place, best combination of lift and drag. As I hope you understood that lift and drag, they are non-linear, non-linear, these dependencies, and moreover, they change significantly with angle of attack, with speed, no, at least drag, and depends on the shape of the airplane. And it's rather difficult task actually to find what is the better, how to select what is the best, most efficient position even of airfoil on the same airplane, because I trust you've seen that airfoils wings, let's say wing stabilizers, they are usually not ideally horizontal in the airplane. They have some preliminary deviation from the horizontal line already, in order to use characteristics of the airfoil in the maximum effective way during the flight, because airplane during the flight, it's no, sorry, that is during takeoff. Somewhere it was during the flight. Airplane during the flight, it's usually in horizontal position, but when airplane at horizontal position, we may already get the advantages of our airfoil, because wing placed with respect to the horizontal axis of airplane with some angle of attack, preliminary already, да, design of the wing. And of course, in this position, also we like to have the minimum possible drag. Polar might have us to select this efficient position of wing with respect to the horizontal plane, horizontal axis of the airplane. And what do you see right now? No, it's just to illustrate you the difference between our understanding, let's say, what how wing looks in streamlines, and something like what we've been talking about, Bernoulli principle. Да? We may imagine that it looks like this: some thin pipes of air, some closed streamlines over and under the surface of wing. And what it really looks like, look, yes, in some cross section of the wing, it's really we have some streamlines over and under the wing, and they will meet only on the trailing edge. They will peacefully meet and peacefully flow next. But in real, the flow over the wing and under the wing, it does not coincide with this direction of the airfoil, and it's like permanently traveling, let's say. It's a bit sliding to the wingtip, to the end of the wing. And as a result, what might happen, not might happen, but what is always happen, it's appearing of additional turbulence flow somewhere in the area closer to the tips of the wing, of stabilizer, of another elements of the airplane. And whatever we discuss here, like ideal case of ideal coefficients of lift, ideal coefficient of drags, in real airplane, it will be different due to shape of airplane and due hundreds of occasional factors that exist in real airplane, including, as I said, even different roughness on the wing, which may be responsible for changing the laminar flow, boundary flow, to the turbulent boundary flow. And what to demonstrate you what it really looks like. No, of course, it's some lucky cameraman has made it. It's not something studied in aerodynamical laboratory, you understand, да? It's real case when airplane take off, maybe somewhere in desert. Maybe it was some another humidity of air or something like this, and he made such a snap, you see, no? No, certainly it's some Boeing, and it's we see it from tail, let's say, from a rear point of this Boeing. You see what really like illustration what these areas over the airplane where the shape of airplane affect to the streamlines and affect differently. You see now how it's flowing different sides, and appearing of vortex behind of tips. Of course, such vortexes exist not only on the tips of the wing, not only near tips of the wing, but tips. The wing creates the most disturbance, let's say, to the air. One more what really effective photo, just to see this effect. You see like airplane pass it through the clouds, and look what it did to clouds. Seems like it's one of bombers, so-called strategical bombers. I'm not sure. Maybe it's Tupolev airplane. Not sure. And I promised you to show a couple more pictures with polars. Let me to recollect. I trust I left it on purpose somewhere. Yep, somewhere here. No, not here. Okay, I do not remember where I took it, where I've seen it. Real polars. Couple more clicks, and if we do not find it, let's forget about it. I'll show you next time. Maybe not even in this presentation about aerodynamics. So, couple more clicks, I already did. Too much materials I'm watching and trying to find something more interesting for you. Well, no, for illustration of my words. What? So as a result, I do not remember where next to find. And already have downloaded the first class for you into your chat. And what I have shown you as books, I will ask the person whom I contacted to, who is responsible in your university for your studying, and I think he will say yes. I will download also to this chat some more books about beginnings, no, basics of fundamentals, about general arrangement of airplanes, and so on. Do understand me correctly. I do not propose you to read through all these books, but I'd like you have these books. in case maybe you need it somewhen, I'd like you to have it. And second thing, I propose you to open different books and to start read them, and just read the one which is more convenient to you, let's say. Maybe some book take your attention due to bright illustrations. Maybe somewhere you would like style of explanation, for instance. Maybe no, some of these books, they are more focused on design. Some of these books, they are more focused on history, for instance, and so on. They are a bit different, those books, and they have range in time of their issuing, time of their appearing at the market, let's say. So if I were you, I would at least look through all these books. I hope I will download them to you. And one more thing I propose you to do right now, the sort of little game. Let's do it together. For instance, we need to create airplane. And this airplane, no, in order it's more simple for us to calculate, this airplane will be for 100 of passengers. 100 people. Let's create airplane. We need airplane sizes. We need airplane, understand airplane weight, and so technical task. Let's create airplane for these people. One more important point when designing of airplane, also you will be given by a range of airplane, not for instance 3,000 kilometers, not far. And next is you will be given the desirable speed of this airplane, the cruise speed of this airplane. No, let it be subsonic. Oh, I forgot to explain what does it mean, subsonic, supersonic. I trust you know it, but I have to explain it. But okay, not right now, next time. And if we're talking about the how to create airplane, first, what we need to understand that one passenger, standard passenger, is around 80 kilograms. No, it's so-called international standard passenger, plus 40 kilograms of his luggage. One standard passenger, together with luggage, 120 kilograms. Okay, what next? What will be the weight of airplane? Because we do remember we have airplane, typically looks like this. Prop, and somewhere inside are passengers and their luggage. Forces. We need to understand what kind of engines we should take. What engines? What is the force of engines should be? We need to understand what is the lift. Lift, gravity. Will not spend time for drawing vector signs. Of course, we have drag and this propulsion force, which is provided by engine. Now, what we may approximately understand, we may understand the weight of the airplane, how much it weighs, how we may understand it. No, actually, we may study statistical data. There are so-called relative weights of airplane. Maybe it's too early for you to understand right now. No, approximately. For each class of airplane, for particular ranges, for particular altitudes, we have already a lot of airplanes, and we may analyze the statistical data and to find some similarities, let's say, between these airplanes. And I know that from statistical data, for instance, that approximately the relative weight of payload for this class of airplane, payload, passengers, together with luggage is around 0.20. 20%. 20% is payload, and other 80% is the weight of structure itself, the weight of engine, crew, how it's fly without crew, yes, fuel, how it's fly without fuel, and so on. Navigation equipment, radio connecting equipment, and so on. Altogether, it's 80% the structure of all the airplane with equipment, and 20% is passengers. No, 20% are our passengers. Okay, if 1/5 of airplane is 100 of passengers, one passenger is 120 kilograms, 100 of passengers is 2,000 of kilograms, 2 tons, 12 tons, yes. And we know that it's approximately 1/5. It means that the whole weight of this airplane is 48 tons. And it means that for horizontal flight, I'm not talking about takeoff, landing, their forces are different, quite clear. For realizing takeoff, you need lift, quite clear, sometimes more than weight of airplane, yes? So takeoff weight is 48 tons, and while horizontal flight, lift should be not less than this 40, agree? As not like this, no? 48 tons. Question is, how to choose engine? How much we need of thrust, how much thrust we need, in order we may move this thing through the air and in horizontal flight. And approximately we need to understand what sort of engine we need. Why I start explaining you this very weird story? Because of these diagrams. These diagrams should help us. And first of them is diagram of aerodynamical quality, polar. Look, we know the lift, yes, and we know the weight. And approximately, now let's imagine that our airplane will be with aerodynamical quality. It does not exist yet, but we will strive to, with aerodynamical quality equal to 10. So we understand that, let me to reduce this in order we may see simultaneously both of half. If we to take color, if quality of airplane equal to 10, and here we have 48 tons of lift is equal to weight, agree? I may use whether 8, whether lift, agree? 48, so here we have what? X, this drag, it's supposed to be equal X. It's supposed to be equal to thrust in horizontal flight. Yes? And here is the question. What they are equal to. And we're already able to understand it. Seems like, wait, we don't need here the equality sign. What supposed be this X, which is equal to thrust in horizontal flight, in case we understand that our assessed takeoff weight is 48 tons, and we understand that quality of airplane we will provide is around 10. We already able to say that thrust should be 8.4. Agree? I hope you will agree. Look, besides of these stories about ideal modes, ideal regimes of flight for that ionized airplane, such aerodynamical characteristics may help us at the first stages of airplane designing. No, right now we will stop it, but I ask you to remember this story about the how to use aerodynamical characteristics and about some another tricks that may be used during designing of airplane. No, it's far yet for us for airplane designing, but whatsoever, I hope you will remember what we've been talking about today. In general, we've been talking about the airfoil aerodynamical characteristic, and it's, as appeared, these aerodynamical characteristics above the all, they may be measured, they may be analyzed, and they may be drawn in the view of diagrams. What they depends on, it's important to understand. Mostly they depends on angle of attack. Mostly, both as aerodynamical characteristics, we agreed to understand the coefficient of lift and coefficient of drag. And I hope you do remember that for, let me to show this, for engineering calculations, for elementary engineering calculations, it might be used those formulas, which are called formulas of Zhukovsky, originally been proposed by Newton, but not in quite the same way they look at Newton explanation. And in these formulas, aerodynamical characteristics Cy and Cx, they characterize the shape of profile. They depends on, they do not characterize, they depends on the shape of airfoil. They depends on the angle of attack in the spatial position of the airfoil. And when it comes about the drag, very important characteristics are appeared also the speed of flight, because they sharply change it with the speed. So drag is much more complex story than even the lift itself. And what also is already studied, and what also we already should understand, that it depends not only those characteristics of airplane as a whole. They depends not only the airfoil shape or fuselage cross-section shape or something like this, but it depends also on general configuration of the airplane, how these airfoils, how they are combined, what are relational. We have not endless wing. Yes, we have some overall sizes of the wing, and this combination of wing sizes, wing shapes, wing as a whole shapes, they are also important, and they affect onto the aerodynamical characteristics of the airplane as a whole. And these aerodynamical characteristics, besides they may be represented separately depending on different factors, they also may be represented in the view of this polar to characterize so-called aerodynamical quality of the airplane. And all those aerodynamical characteristics, they are necessary for us. They are necessary to know what for, to design our airplanes. But in future, knowing these aerodynamical characteristics, we are able step by step to pass to the from idea or from our commercial need. I need airplane for 100 people, for instance, to some more practical stages, to some stages of airplane design. Let's stop on this. To meet next time.